Let us now look at the charging and discharging process of a capacitor, okay? How do we charge a capacitor and how can we discharge it? We have a circuit here that shows the arrangement. The circuit contains a high impedance voltmeter, it contains a capacitor, it contains a high resistor. Of course, this offers the resistance that opposes the flow of current. That is why the charging and discharging process of a capacitor is exponential. It's a gradual and continuous process. In fact, in the curve of the charging and discharging process, it goes this way exponentially for the charging process and then this way exponentially for the discharge process. It's not a linear, it's straightforward something, okay, as if it's a solid, fast charge and discharge. No, it's a gradual process. We refer to it as an exponential discharge or charging process because of this high resistor value. Okay, now we have the key K. This key is a two-way key. It can be connected to point B, which leads to the charging process. It can be connected to point A, which leads to the discharge process. Then of course we have the battery here. Okay, now during the charging process, what's going to happen? Let's consider the charging process first. To charge, we're going to connect this key K to point what? B. Once that is done, then this circuit, that is this capacitor itself, would have been connected to the battery. You can see that, right? To be connected to the battery straight, and then the charging process will begin. How do we know that the charging has begun? The high impedance voltmeter here will begin to read. Okay, if it begins to read, we'll be seeing a rise, tickling, increasing in its value. That shows that the charging process has begun. And this will continue, it will continue reading, meaning that the capacitor is charging until it will get to a point and become steady. It will no longer increase, it will no longer decrease in its value, in its reading. At that point, we now say that the capacitor is what? Charged. Take note that the capacitor is connected in parallel with this high impedance voltmeter. And of course, we want to look at what happens during the discharge process now. In the discharge process, all you need to do is to disconnect this key from point B. You disconnect it from point B and connect to what? Point A. Take note of what happens. Once you connect this to point A, this will now be our circuit. Are you seeing it, right? That will be our circuit. The battery has been what? Disconnected. That's the point there. And so there is nothing that is going to provide charge that this capacitor will store, which therefore means that the process will lead to discharge. And because this connection is through this high resistor, then the charging stored in this capacitor will start discharging. So that's really what happens. In the discharge process again, it is through the high resistor. Take note of that, said that before. Now what's going to happen? How do we know that the capacitor has begun to discharge? We see the voltmeter reading. It will start decreasing. Remember, in the charging process it increased. So this time around, the value of the voltmeter reading will start decreasing. We know that the discharge process has started. And that it will discharge up to a point and then reads 0. Once the voltmeter reads 0, okay, then we now know that the capacitor has been discharged fully. So that's what really happened in the charging and discharge process. In the next video, we're going to look at the graph of this charging and discharge process, and of course derive an equation leading to the time constant of the discharge process. We now want to look at the curve for the charging and discharge process of a capacitor. And we have this diagram on the board. You see clearly that the curve is an exponential curve. It's not a straight line curve, okay? When the key was connected to point B, as we saw previously, it is circuit. So you notice that the charging began, and the charge build-up is with respect to what? Time. Is that okay? Let us say as time is counting from the initial time 0, the charge will start building up in the capacitor. And you know that the charge build-up is as a result of the current supplied by the battery, okay? Which means that the charge stored by the capacitor is directly proportional to the current supplied by the what? Cell. That's the battery. And that's what we have here. Charge is directly proportional to what? Current supplied. And this happens with what? Time. Which means that as time increases, the charge buildup will increase as the battery supplies more current. we stated that this is an exponential curve already. Now look at between this point BA, there is no charging, there is no discharging. That simply shows that the capacitor has been fully charged. It happens when the voltmeter reads the maximum value of the battery. Is that okay? That point where the voltmeter becomes what? Steady. It's no longer increasing its value. It means that the capacitor is fully charged. So take note, between point BA, this shows what? Full charging. Full what? Charging of the capacitor. Take note of that, please. That's when the voltmeter reading becomes steady. Then at point A, what happens? Recall from the diagram before now, we saw that in the circuit, when you want to discharge, you connect the key to point what? To point A. Then the discharge process will begin. Again, the discharge process is an exponential curve. Is that okay? It's a gradual process since the charging and discharge is through a high resistor. Okay, now once the charging has been complete, of course you know that the capacitor would no longer have any charge. The voltmeter will be reading 0, which corresponds to this point where the discharge curve line touched the t-axis. If you read it off here, it is what? 0. Now at this point you have maximum charging, even maximum charging from here, the discharge process begins. Now we've stated already that the charge buildup is directly proportional to current supplied by the what? Cell. The sign of proportionality we might wish to introduce here is time, so that Q will be equal to IT. Look at it from this equation 2. Does that make sense? Now we want to establish something, a time called a time constant is equal to the capacitance of the capacitor times the resistance of the resistor. Now how do we go about that? You see, we know already that charge is equal to capacitance times what? Times voltage. We obtained that when we were treating capacitance of a capacitor. We also know from Ohm's law that voltage is equal to current times what? Resistance. That being the case, we can substitute for this voltage, okay? In place of this voltage, we put IR. If we do that, our charge will now be equal to I times C times R. That's what we're going to get here. That is, in place of this V, we put this IR. Then we'll get this equation 1. Now, since we know that charge is directly proportional to what? Current, we can introduce time as our proportionality constant, and that will give us equation 2 here. Removing this sign of proportionality, introduce equal to and a constant t. Now, we can compare equation 1 and 2. If you compare equation 1 and 2, this is Q to Q, they take care of themselves. This is I to I, take care of themselves. You notice that T is equal to what? CR. Which means that time is equal to capacitance times what? Resistance of the discharge process. And this T is called the time constant. In the next video, we are going to look at the exponential decay equation for the discharge process. The exponential decay equation for the what? Discharge process. In that equation as well too, we are going to determine the value of the charge at discharge process when half of the charge in the capacitor may have been discharged. We are also going to see the value of the charge, okay, in the capacitor when 37% of the charge originally stored in the capacitor may have been discharged. In this video, we now want to look at the equation of the exponential decay of the discharge process of a capacitor. You will recall in the previous video, we looked at how to charge and discharge what? A capacitor. So this time around, we want to focus on the equation that models the discharge process. Now, how do we start with? We look at the fact that charge is equal to capacitance of the capacitor times what? The potential difference. Recall that the capacitance of the capacitor is equal to the charge stored divided by potential difference. So you cross multiply, you have this. We also know from Ohm's law that the potential difference, voltage is equal to current times what? Resistance. If you substitute for voltage here, we're going to get that charge is equal to current times the capacitance of the capacitor times the resistance. Does that make sense? Now, from calculus, we have this equation. That is the rate of change of the charge stored by the capacitor with respect to what? Time. Recall that charge is equal to what? Current times time. During the discharge process, we know that the capacitor loses charge with respect to what? Time. And because the charge is being lost with respect to time, we introduce the negative sign here. So the negative sign actually tells us that the charge stored in the capacitor is decreasing with respect to time. And you know, when you want to show the relationship of a quantity with respect to another, you can use differentiation. Is that okay? So the differential calculus for making current subject to the formula here would be the rate of change of charge with respect to what? Time. Introducing a negative shows that there is charge decrease because you are discharging. If it is a charging process, then there will be no need for what? This negative. This equation we are about to derive is a decay process. Is that okay? An exponential decay, so there's a reduction. Now let's move on. If we know that current is equal to negative dq over dt for the discharge process, then all we now need to do is to substitute for current in equation 1. So we're going to put negative dq over dt for I here, and if you do that, we'll get this equation. It's going to be q equal to negative dq over dt times cr. You can see that. This equation is a first order differential equation. In fact, this equation is a separable variable differential equation which can be separated and integrated. Why do we separate this? We have two differential coefficients there. One with respect to q, the other with respect to t, time. So we're going to separate the charge variables and the time variable. Take note that this CR is a time factor. Previously, we referred to it as what? Time constant. It means that we're going to take this dt and CR to one side of the equation, then q and the differential coefficient dq to one side of what? The equation. Now I chose to transfer this dt to the left hand side. If this dt is moving to the left hand side, it's going as numerator because you're cross multiplying. Is that okay? Then this CR going to the left hand side is coming as denominator because here it is a numerator. Does that make sense? So everything would be like dt divided by CR, which is the same as 1 over CR times what? Dt. Then this q would have to be separated to come to its controlling differential coefficient dq. This q is numerator here, so if it's coming to the right hand side, it's coming as a denominator, which is 1 over q dq. Or you can simply write that as dq over q. So that's what we have here. Once we've separated these, look at the separated variable. It now gives us room to integrate. Now you take note. In integral calculus, once a variable is multiplied by a differential coefficient, maybe this or the other thing, right? It gives you room to integrate. For you to obtain the value of that quantity, you have to integrate. So at this point, we're going to integrate this equation and then look at it. This 1 over CR is a constant. This CR is called the time constant. Capacitance of the capacitor times the resistance in that circuit is a constant. And so we're going to bring it out of the integral sign. Then we'll now have integral dt. Integrating from the limit when time is 0, that is when you've not started the discharge, up to a particular time when you have started the discharge what? Process. Then coming over here, from charge Q naught, that is the charge in the capacitor when you have not started the discharge. Alright, we refer to it as Q naught, the charge at time 0. Is that okay? Down to the final charge Q when you have started what? The discharge process. This Q can be for any particular what? Time. So integral of it, 1 over Q dQ. Look at it. Now in integration, if you have integral dt, it's going to give you t. Is that okay? We encourage you to visit our YouTube channel at GMAETS41 and subscribe to it. You have a piece there in integral calculus that will guide you on why integral of a differential like integral dx will welcome back your variable x. And so that integral dt will welcome back the variable t for us. Is that okay? So integral dt will give us t. Take note, it's not dt that integrated. You can't integrate a differential coefficient. They are only directing you what to integrate with respect to. Is that okay? So please visit our YouTube channel. Let's move on. This will give us integral dt, which is t from 0 to time t, equal to integral 1 over q. If you differentiate this q with respect to q, you are going to get what is in the numerator. By use substitution of integration, such integral is going to give you ln of the denominator. So look at it, ln q. Then with the limit from q naught to what? Q. What do you do with limit of integration? Remember, this is a definite integral. That is why you have limit. If there is no limit of integration like this 0 to t, q naught to q, then after integrating we'll put plus c. Is that okay? But since this is a definite integral, we're going to apply our limit of integration, no need of plus c. So we are going to substitute upper limit for what we got here minus lower limit. Is that okay? Now, in place of this t, now if you put this upper limit for t, in place of this t, you're going to put t, then minus, go back again, in place of this t, you put lower limit 0. You see that is going to be t minus 0, and t minus 0 still give you t. That is why from here we have t times 1, which is t over cr. Then coming over here, in place of this ln q, this q, substitute upper limit. You are going to get what? Ln q. Go back and do subtraction, then substitute lower limit for the q. You're going to get ln q naught. Is that okay? That is it here. Then from this part, we apply the law of logarithm. Because ln is logarithm to base e. And you know that when you are subtracting logarithms that have the same base, all you need to do is pick one of the logs and then divide the numbers. Is that okay? So that gives us negative. I picked one of the ln. Then this is the numerator, the first number divided by the second number, q naught. So this is the equation we'll arrive at. And then to remove this ln, we are going to take exponential of both sides of the equation. But before doing that, let's multiply both sides by minus 1. If you multiply both sides by minus 1, this negative will come to this side. Is that okay? So that you have something like ln q over q naught, alright, equal to negative t all over cr. Then taking exponential, you get q over q naught equal to exponential negative t over cr. Exponential raises a term as to power, right? So that's what we have here. And then making q subject to the formula, you cross multiply, you get this equation q naught exponential minus t over cr, which will label as equation 3 star. This equation is what is referred to as the equation of the exponential decay of the discharge process. This q is the final charge at any given time t, while this q naught is the initial charge before the discharge process. In the next video, we're going to look at the half-life, alright? What charge will be left when this t, alright, is the half-life time. And then we're also going to look at what charge will be left, alright, when this t approaches a certain value where you will get 37% of the initial charge left. We now want to look at the half-life of the exponential decay of the discharge process. Generally, half-life of any substance or material is the time taken for the total quantity of that material to reduce to half of its original value. Alright, so defining half-life in terms of the discharge process, it is simply the time taken for half of the charge stored in the capacitor to discharge. That is to say, for half of the charge stored in the capacitor to reduce. Of course, if half reduces, then half will be left. Which therefore means that we can state that Q, which is the final charge left during the discharge at half-life, will be equal to 1/2 of the initial charge. Simply half of it, okay? We are representing T now with T half. Now that being the case, let's go back to our equation 3, where we obtain that Q is equal to Q naught exponential minus T over CR. You know that this is the equation that models the discharge process of the capacitor. Is that okay? So in place of T, we are going to represent it with T half. Then in place of Q, we are going to replace it with 1/2 Q naught. Look at that. And once that happens, you notice that this initial charge present will cancel out of the equation. 1/2 will now be equal to exponential negative T half divided by what? CI. Now we are going to remove this exponential from this equation, and to do that we'll take ln of both sides. Is that okay? So look at it. If you take ln, this exponential will disappear. You introduce the ln to the half. Now cross multiply, get the ln of 1/2. Ln of 1/2 is minus 0.693. Look at it. Times CR if you cross multiply. Multiply this equation by -1 or divide it through by -1. You would arrive at equation 4 star. That equation 4 star, very important. It is the half-life of the decay process. Is that okay? So if you're asked to calculate the half-life during the discharge process of a capacitor, this is what you use. Now we want to work on this equation more. Is that okay? We want to obtain the time during which the final charge left will be 37% of the original charge. That's of the initial charge during the discharge process. To arrive at that, what do we do? We need to recall that we stated that T equal to CR, and we call the time constant. So we're going to come to this equation. In place of this T, we'll replace it with CR. And of course, if you do that, you would have CR divided by CR, which if you divide, you're going to get exponential minus 1 left. Look at it. Okay? And mathematically, using negative index law, that is a reciprocal law of indices, you know that this is the same as Q naught times 1 over exponential 1, right? Does that make sense? Now, everything will be equal to Q. And then exponential 1 is a constant. It's equal to 2.718. So if you press 1 over 2.718, it's going to give us 0.368. Alright, which I can still write approximately as Q equal to 0.37 Q naught. Does that make sense? Now if you multiply this 0.37 by 100, you get a value in percentage. And that is why we have equation 5 star Q is equal to 37% Q naught. And what does that tell us? Question 5 simply shows that CR, that is the capacitance of the capacitor times the resistance produced by the resistor you use during the discharge process, is the time taken for Q to fall to 37% of the initial charge. In the next video, we're going to look at how to compare capacitors and of course solve problems regarding capacitors in series and in parallel.